The second video for Chapter 6, Background Information, is going to have us looking at the different strengths of acids and bases, how water behaves when looking at acid and base systems, and the pH scale. So on this slide, there is a list of acids and bases, and then we've got the red on the left showing the strength of the acid. With the darker the red is a stronger acid. And on the right, the blue is representing how strong a base is. Now, this is not a comprehensive list of all the acids and bases that exist. Nope. This is just some of the more common ones that we're going to be looking at. This table will be given to you in class. It is also in the Canvas shell. And these are not tables for you to memorize. We're just going to learn how to use this table. So we can, in Chapter 15, you looked at how the value of the equilibrium constant, the K value, if it was really big, that meant that products predominated, that at equilibrium there were more products. And if the number itself was really small, that meant that at equilibrium there were more reactants, so the reactants predominated. So in order to figure that out, we needed to know the value of K. Is it real big or real small or what? This table lets us predict for an acid-base reaction which side that will predominate, which there will be more of reactants or products at equilibrium without any numbers, just by having this table. So that's the purpose of this table. And again, you don't memorize this table. You would always be given this table like on exams or on questions. So it's just learning how to read it and to use it. Now, one thing I want you to notice that the acid and base columns, on the acid side and the base side, it shows a conjugate acid, and right next to it, it's conjugate base. So they're paired up as conjugate pairs. So like HCl is the first acid listed. We can tell by the color of the red that it's the strongest acid on this table. Now, if you look at the Cl minus, the chloride, its conjugate base, you can see that on the base side, the strongest ones are on the opposite end, on the bottom. And so the Cl minus is the weakest base on this table. They actually even say that it's negligible, which means we're going to learn at the end of this chapter that we're not even going to consider chloride a base because it doesn't accept protons. So it's not really a base. So a real scientific and classy way that I think of this is that if you have a strong acid, its conjugate base is a shitty base. If you have a strong base, its conjugate acid is a shitty acid. If you have somewhere in the middle, like the weak ones, so like H2S, hydrosulfuric acid, and HS minus, hydrogen sulfide ion, they're about pretty much in the middle. So the H2S is a weak acid and the HS minus is a weak base. So the other way to think about it is there's a checks and balances for this. If you have a really strong acid, to balance that, its conjugate base is really small. If you have a really strong base, to balance that out, its conjugate acid is really weak. If you have somewhere in the middle, then the weak acid and the weak base are both kind of in the middle, average weak. Okay. So the water, the H3O plus and H2O are boxed in this, and then at the bottom, H2O and OH minus are boxed. That's just to point out that water is listed in two places on this table. And remember, water is amphiprotic, meaning it can be an acid or base depending on the situation. If you're looking for water as it acts as a base, you need to look in the base column. If you're looking for water when it acts as an acid, look in the acid column. So just make sure you keep those straight. So something we're going to look at in more detail later. So strong acids, they're strong because they 100% ionized in water. They dissociate, they break apart, they donate their protons 100%. And strong bases accept 100%. So this is an example of an acid-base reaction. And what we would want to do here is using that table that we have. So I'm hoping that you either have a copy in front of you, the one that I gave you in class, or you've looked up the one from Canvas so that way you can have that in front of you as well. We're going to look at this reaction and practice identifying what is an acid and what is a base on both sides. And then we're going to use the table. So this is a good reminder of how to use the Bronsted-Lowry definition to figure out if something is an acid or base. So first, I'm just going to count the hydrogens on everything. So the chlorine has 1 hydrogen, the oxygen has 2, this oxygen has 3, this chlorine has 0. So looking at this chlorine from before and after. It starts with 1 hydrogen and ends with 0 hydrogens, so it donates a hydrogen. So I'm going to label that as an acid. The oxygen starts with 2 hydrogens, ends with 3 hydrogens, so it must accept a hydrogen. So I'm going to call that a base. Now I know this arrow is only going left to right, but let's go ahead and classify products as if the arrow was going the other direction as well. So if we look at oxygen going from right to left, it starts with 3 hydrogens and ends with 2 hydrogens. So it donates a hydrogen, so that makes it an acid. Cl- starts with 0 hydrogens and ends with 1, so that makes it a base. Again, if you notice this, the HCl, its conjugate is the Cl-, so if HCl is an acid, Cl- is going to be base every time. Water was designated as a base, so what it is on the other side is its conjugate acid. So what we need to do right now is go to that table, and we're going to look up HCl and H3O plus on the acid column, and using that table, decide which one is stronger. If we look at that, HCl is the very top thing. H3O plus is still pretty high, but not all the way at the top. So HCl is a stronger acid than H3O plus. I'm going to write SA here and WA, just standing for stronger acid, weaker acid. And then we're going to go on the base column and look up H2O and Cl-. Well, Cl- is the worst base of all of them. So H2O is the stronger base, and water is the, or Cl-, I'm sorry, is the weaker base. So you notice that there's a strong side and a weak side. So the strong acid and the strong base are on the same side, and the weak acid and the weak base are on the same side. Always going to work out. So technically, you only have to look at either the acids or the bases to get the information we need for this problem, because if the strong acid is on one side, then the strong base will be on the same side. I do both just to make sure I don't screw something up. So hopefully we're feeling all right on identifying the strong acid and strong base and weak base in the reaction. So then what we can use with this, whichever side is the weak side, so that's this side in this problem, the weak side is going to be the side that there is the most of at equilibrium. So the weak side is the product side. So at equilibrium, there's going to be way more products than there are reactants. And it works that way is because the strong side, they're strong, which means they react. They react, maybe not all the way. In this case, it'll be all the way, but they react more than the weak side does. So since they're more reactive, there are less of them left. So the weak side, that's the side that there is the most of. So in this reaction, the weak side is the products. This reaction is product favored. It would have a very large equilibrium constant. It's actually so large. That's why it doesn't show the equilibrium arrows. It just shows it going left to right, because this reaction goes to completion, like goes a limiting reactant until one of the reactants is gone completely. So we're just going to practice this. Again, you're going to need that table in front of you so you can reference to see what is strongest. So this reaction, one thing about the acid here on the left, we'll see that in just a second, but in Gen Chem 1, you might have seen CH3COOH listed, or HCH3COO, or HC2H3O2. All three of these are acetic acid. They're all the same compound. It's just how they're written. So the first one I wrote down, the CH3COOH, is actually the most correct version. That's like showing you how the atoms are attached to each other. But a lot of times people write it with the H out front. So the second one, HCH3COO, because it's an acid, and we recognize acids because they start with hydrogen. So that kind of fits that. The condensed formula is the HC2H3O2. The acetate polyatomic ion can be written two ways, so that's one. For whatever reason, our textbook, when using acetic acid in part of this chapter, uses it the way it's written in this equation. So that's the reason why I left it that way, because sometimes you see it that way. It's just another way to write CH3COOH. They just combined the two O's and put a subscript to them there. Whatever. The reason why I'm pointing this out is because on the table that we're going to look at in just a second, the way it's written in the equation is not the way it's written in the table. It's written in the table this way. So it's weird. This is the only one that you see that happen to, but if I were you, I would take that table with the acids and next to HC2H3O2, write down all of these other possible formulas, just to make sure you don't get freaked out when you can't figure out what's going on. So what we're going to do now is we're going to look at each chemical in this reaction. We're going to count the hydrogens, identify what's an acid, what's a base. Then we will look at our table to compare the two acids to each other to see which one is stronger, compare the two bases to each other to see which one is stronger, and then decide which there is more of. So starting at the left, there are 4 hydrogens there, 2 hydrogens here, 3 here, and 3 here. So we're going to compare. So starting with the acetic acid, it starts with 4, it ends with 3, so that makes it an acid. Water starts with 2, ends with 3, so that makes it a base. And we can see that this works out, but we're going to see that since water was the base, the H3O plus is its conjugate acid. Since acetic acid was an acid, the acetate ion is a base. So we would go to our table and look up the acetic acid and H3O plus on the table. And it turns out that H3O plus is stronger. So I'm going to write strong acid, weak acid. And then we would look up the bases. So water on the base side and acetate on the base side. It turns out that acetate is a stronger base than water. So strong base, weak base. So we have now figured out which one is which. The strong side is on the right and the weak side is on the left. So what we're looking for is the weak side. So the weak side is on the left. The weak side is the side there will be more of. So there will be more products, which means the reaction is shifted to the left and that the K value is very small. So at equilibrium, there will be more reactants. I don't know what I just said. Did I say products? I meant reactants. I don't know. There will be more reactants because it's on the left-hand side. Okay, so looking at these two, let's see what we can do. Again, we're just going to identify the acid and the base, use the table to figure out what's going on. So 1 hydrogen, 2 hydrogens, 2 hydrogens, 1 hydrogen. So HPO4 negative 2 goes from 1 hydrogen to on the right 2 hydrogens, so that's going to make it a base because it accepted. Water goes from 2 hydrogens to 1 hydrogen, so it donated, so it's acid. So this will be the acid and this will be the base on the other side. So we're going to look up water on the acid side and dihydrogen phosphate on the acid side. And dihydrogen phosphate is the stronger one, so stronger acid, weaker acid. Technically, we know right now which is the strong and which is the weak side, but let's go ahead and double check the bases as well just to make sure. I'm going to compare OH minus on the base side to hydrogen phosphate on the base side. So strong base, weak base. So this reaction will have more reactants and will be shifted to the left. Oops, didn't mean for that to happen. All right, and then the second reaction, we've got to count the hydrogens. So 4, 1, 3, 2. So ammonium goes, so the nitrogen has 4 hydrogens to start with, 3 hydrogens to end with. So it's an acid because it donated. Hydroxide starts with 1 hydrogen, ends with 2. It's a base. So those are the other side. We would look up an H4 plus and water on the acid column. So stronger acid, weaker acid. We'd look up hydroxide and NH3 on the base. So stronger base, weaker base. So with this reaction, there are going to be more products because that's the weaker side. The weak side is the one that there's the most of. So it'll be shifted to the right. So again, these types of questions, you're always going to have the table in front of you. You just need to make sure you can identify all the acids and the bases and then use the table to figure out what's stronger and what's weaker, and then know what that means. That once you figure out which one's weaker, that's the side there's the most of. So now that we've used the table, we're going to look at how water behaves with acid and base stuff. H2O is amphiprotic, which the other word is amphoteric. You can see that up here, which means sometimes it acts as an acid and sometimes it acts as a base. It can do either one. So in this reaction, it's just showing 2 water molecules, and just having 2 water molecules present without anything needing to happen, they will automatically go to equilibrium where one water molecule will serve as an acid and the other one will serve as a base. So one will donate a hydrogen and the other one will accept it. So if you count the hydrogens and oxygens on the left and the right, they're all still there. Hydrogen has just moved. So since this happens automatically, this is not a you have to push a go button or put it on the hot plate or add another chemical. Water just does this. It's called auto-ionization because it automatically ionizes without being forced to. So this is an equilibrium process, which means we can write the equilibrium constant expression for this reaction. I'm going to go Kc. So product over reactants. So H3O plus, the molarity of it to the first power, times hydroxide, the molarity of it, the first power. So that's the products. If I do the reactants, if you look though, H2O, they're liquids. And if you remember liquids and solids, we just either ignore them or say they're equal to 1. So it's like this is over 1. So we don't really have to write the over 1 part, but that's the equilibrium constant expression. Okay, so that's where that came from. So we talked in chapter 15 how equilibrium constants are not always the same. They change for every reaction and they change at every temperature. So that means that the value for this equilibrium constant expression isn't the same all the time, but we are going to pretend like the world only happens at 25 degrees Celsius because we're going to use the equilibrium constant happens at 25 degrees Celsius. At 27 at whatever, we have different values for that. So we're just going to pretend like everything happens at 25. So instead of writing Kc, the constant is going to be abbreviated Kw, W for water. So we can just plug that number into this equation. So this is our first new math equation of the chapter. 1.00 times 10 to the negative 14 equals H3O plus times OH minus. So we're going to come back and use that in a minute. Our second new equation of the chapter is pH. So pH is a scale that lets us know how acidic or basic something is. It is not the only scale that does this, but it's the only one, well, the main one we're going to use. The equation for pH, it's a base 10 log, so it's not the natural log, the ln stuff we used in chapter 14. This is base 10 log, so look on your calculator, there's an log button. The inverse of log is 10 to the x. So that's how we undo that. So this is the equation for pH. pH equals the negative log of H3O plus. Just remember, brackets mean molarity. So in this equation, you have to plug the H3O plus in as molarity, not moles, not grams, not milliliters. It has to be molarity. And actually going back, the equilibrium constant expression, it also has to be molarity. Okay. So the pH scale, or looking at this, all I did was took the equation for the equilibrium constant expression of water, and then if we had pure water, that would mean we have the same number of H3O pluses as we do OH minuses, because for every one water that breaks apart, we get one H3O plus and one OH minus. So if we use that information and solve for H3O plus, that's where the 1.00 times 10 to the negative 7 comes from. Plugging that into the pH equation, we get the value 7.000. That's why in the pH scale, 7, the pH of exactly 7 is considered neutral, because that would be pure water. Now, honestly, you've never had pure water. The DI water we use in lab is probably the closest, but it's still not pure water. So the pH scale, we're assuming everything's at 25 degrees Celsius and that you would only get a pH of 7 if it's pure water. So just letting you know that you've not experienced that. So on the pH scale, 7 means neutral. So it's pure water. It's not acidic, it's not basic. Any value less than 7 is considered acidic, so the solution is an acid. Any value on the pH scale greater than 7 is considered basic. So most of the time when you learn the pH scale for the first time, you're told that it goes between either 1 and 14 or 0 and 14. Yeah, that's crap. The pH scale is whatever number it needs to be, which means it's possible to have a negative pH value, possible to have a pH value greater than 14. There are some pHs that are like 25 or 32. So the pH scale is not limited to 14. I think people say that because 7 is half of 14, and so it makes it easier to remember that 7 is neutral. But really the rule is 7.000 is neutral. Below 7, acid. Above 7, base. The further away from 7 you are, the stronger it is. So a pH of 1 is more acidic than a pH of 4. Both of them are less than 7, but the further away from 7 you are, the stronger it is. 1's further away from 7 than 4. Same thing with base. So a pH of 10 and a pH of 15. A pH of 15 is more basic than a pH of 10. Okay, so that's our pH scale rules that we have. So this is just for funsies. You're not memorizing this. This is just a list of the value of things, the pH value of things that you might run into on a daily basis. So gastric juice, yeah, that's tummy acid, like when you throw up, that kind of stuff. It's mostly salt and water and hydrochloric acid. So unsurprisingly, it has a very low pH. Lemon juice is also very acidic. Vinegar and cola, like carbonated beverages. Well, carbonated beverages have CO2 in them. CO2 mixed with water makes carbonic acid. So bam, acid. Wine, tomatoes, coffee, like you hear the commercials talking about how acidic coffee is. They're not lying. Rain. So this is not what people call acid rain, but regular rain has a pH of like between 5 and 6. So 5.5, 5.6. So this is something that bothers me, and I have no idea why. So acid rain is when the pollution in the air, the NO2 and more CO2 gets absorbed in the water in the clouds. So that way the water becomes nitrous acid and carbonic, like a mixture of nitrous and carbonic acid. So that way our rain is more acidic than normal. So acid rain has a pH of like 4. Normal rain has a pH of like 5 or 5.5. I don't know why it bothers me, but I hate that people call it acid rain. It'd be like more acid rain, because regular rain is acid rain, but whatever. That's really dumb. It's just an issue of my own. Baking soda is a base. Probably the most basic thing in your house. Probably Drano or whatever you use if you've got a clogged drain. It's usually a mix of sodium hydroxide and bleach. So 2 very basic things, probably the most basic things. So bases are slippery when you touch them, and acids are gritty when you touch them, like if you rub them between your fingers. So again, you're not memorizing any of this, but some ways that acid-based stuff is in your everyday life is when you have heartburn. That means your gastric juice, this buddy. There's too much going on in your stomach. You've got more gastric juice, you've got more acidity in your stomach than you need. You need acid in your stomach, but if you have too much, then it starts moving up, and that's when you feel the pain and you feel the heartburn. So the Tums or Maalox or whatever the stuff that you take when you have heartburn is a base, because the acid and the base will react, and the base will cancel out some of that acid. So you take the correct amount of base, so that, like Tums or whatever, so that way it doesn't neutralize all of the acid in your stomach, because you do need acidity in your stomach. My grandma refuses to, as she says it, spend money on Tums, so she just eats a spoonful of baking soda when she has heartburn. So 2 things, that's gross. And also it's not measured out well, so that does the job. It neutralizes the acid in her stomach, but it probably neutralizes way more than it needs to. So just a piece of advice: don't eat baking soda when you have heartburn. It's gross, and it's probably not good for you, because I don't know if you take too big of it just, ugh. Okay. Anyway, pH scale, we're going to practice doing the calculations in class, so we won't do that on here, but hopefully you have a background for some more of the acid base stuff.